Hi there, my name is David and I will be exploring with you our UI dataset, MUD, as part of our project, MUD towards a large-scale and noise-filtered UI dataset for modern-style UI modeling. Firstly, let's establish why UI datasets are important. UI datasets can support numerous applications in working with user interfaces, including UI element detection, screen embedding, widget captioning, icon labeling, screen summarization, and more. All of these have the potential to assist research and development into making better user interfaces and improving accessibility of applications. When it comes to UI datasets, they usually consist of two main items: the screenshot and the view hierarchy, which is essentially the UI elements on the screen encoded in a programmatically readable format. The view hierarchy contains information about each element's type, any text, its position, and any other relevant metadata, such as the element's type specific to a platform. Together with the screenshot, UI data can be stored and read in a visual or programmatic form, useful for example, training visual models. Before we embarked on the creation of our dataset, we explored existing datasets through an empirical study of the RICO dataset, a well-known, widely used, and large-scale UI dataset from 2017. The study involved 132 apps from RICO. Annotators obtained 82 pairs of UI designs, one from RICO and one from a recently taken screenshot, and compared them. Overall, we found four main differences in the current apps compared to those in the RICO dataset. First is a new visual appearance. Colors, shapes, layouts, padding, and the general design language appear to have changed since RICO. With the changes in design language trends, rebranding, and more, lots of apps have a new design in line with current trends and brand image. Visual hierarchy has also changed. More specifically, a focus on accessibility, reachability, and readability. This results in new and different layouts of UIs. Some apps have changed the way users interact with them. These mostly revolved around a better user experience. For example, a more intuitive calendar picker that resembles a physical calendar as opposed to number pickers. Finally is new typography. Stylistic choices like the use of typeface has influenced the appearance of many apps. Next, we explored any noise that existed in the RICO dataset through another empirical study. 500 randomly selected UIs from the RICO dataset were given to annotators. Annotators would select the type of noise that is in the screenshot, if any, such as partially rendered UI elements, overlapping bounding boxes, inaccurate bounding boxes, and others. In summary, we found three key sources of noise. Firstly, there were screenshots whose bounding boxes did not match the screenshot, likely due to partially rendered UIs at the time of capture. This leads to UI elements that belong to two different screens appearing at the same time, and/or bounding boxes that do not match the element in the screenshot. These inconsistencies can introduce unwanted noise in the dataset. Next is overlaid view hierarchies. There are often UI captures of bounding boxes from two screens, often overlays, appearing at the same time. This results in phantom or ghost bounding boxes for non-existent UI elements in the screenshot, and/or bounding boxes that have lots of overlap. These overlaps and inaccuracies can significantly impact a visual model's understanding of the user interface. Finally is duplicated UIs. There were many UI captures that were very similar, if not identical. Although these are not inherently troublesome if they are accurate, it introduces redundant data into the dataset, and any inaccuracies that are present, even small, can build up as noise. Altogether, outdated UIs and noise in the dataset can significantly affect data-driven modeling. Outdated UIs can become irrelevant for a model. Noise can introduce inaccuracies into any data-driven model, giving incorrect training data. To address these issues with existing datasets, we set out to create our own dataset with a focus on breadth, coverage, and accuracy, that is, less noise. Towards our goal, we set out several steps. Firstly, crawlers found a set of apps from the Google Play Store, which form the basis of the apps in our dataset. Since the quality of apps can influence the quality of its UIs and thus the quality of our dataset, we aimed for more popular apps, which tend to be of high quality. Secondly, we created a large language model powered, or LLM powered, explorer that automatically explored the apps installed on Android devices to collect screenshots and view hierarchies. This allowed for large-scale collection of data independent of human labor and time. More on this later. Thirdly, we validated and refined the dataset to remove noise. This involves some automated steps to filter out issues with view hierarchies, then, as a final defense mechanism, a human validation step to catch any issues that were missed in the automated ones. During exploration, the LLM helped guide the explorer to make intelligent steps, with the goal of achieving maximum coverage in the apps. The LLM was given this prompt to give it context of its goal, sort of like a system prompt. When encountering a screen in the app, the explorer asked the LLM, given the view hierarchy, how it would navigate the app. To ensure the response was uniformly understood by the explorer programmatically, we asked the LLM to respond with a specific syntax. This allowed the explorer to take logical and informed actions in the app, such as entering specifically formatted text and tapping buttons in a specific order, all with much greater intelligence compared to a random explorer. Despite the use of an LLM-powered explorer, some challenges during exploration still remained, which affected the amount of noise in the data. First is partially rendered UIs. This can occur when a device has not fully rendered the UI yet, and the explorer takes a capture, resulting in a screenshot between transitions and a view hierarchy that does not match the screenshot. This was overcome by tweaking the explorer to remain on screens for longer before taking a capture, to ensure what's on the screen is in sync with the accessibility service that actually captured the view hierarchy information. Despite the efforts to reduce partially rendered UIs, some residual noise remained. One of this was an overlaid view hierarchy. This could be the result of various factors, such as partially rendered UIs, app overlays not coded properly, or non-standard handling of in-app UI elements. To help mitigate this issue, a model was trained using ResNet that determined the correctness of the bounding boxes in screenshots visually, that is, whether it was misaligned or overlaid. This reduced the number of screenshots with inaccurate bounding boxes. Thirdly is the issue of duplicate UIs. Sometimes the exploration may come back to the same screen and take a capture. To identify and remove these duplicates, a hash of the view hierarchy metadata was computed and compared against others to identify potential duplicates. Now, let's discuss the performance of this LLM-powered explorer. We got 30 apps and ran our explorer against 3 state-of-the-art baselines, Monkey, Droidbot, and Humanoid, which are widely used explorers. Compared to these baselines, our model outperformed in activity coverage, achieving an average of about 60% coverage compared to 30, 35, and 45% in the other baseline explorers. This shows that our explorer is more effective at exploring apps and covering more of the app. Our LLM-powered explorer comes with several significant advantages that improve the exploration coverage and reduce unwanted noise. Firstly, the LLM can read and understand text input requirements from on-screen instructions, such as email addresses, phone numbers, names, and even all of these with specific formatting requirements. While traditional explorers can incorporate hard-coded input values based on text input types inferred by the metadata, it is much more limited compared to what an LLM can understand and generate. Having valid data can help the explorer be more successful in navigating input-based screens, and thus more likely to have a greater coverage of the app. Next is being able to understand and provide sequences of actions in contexts that require it. For example, having to check a box to agree to terms and conditions before pressing a button to continue, or other screens that require actions to be done in a certain order to proceed. Screens that require this sort of sequential execution are much more likely to bog down random explorers as they need to hit this combination of actions by chance. In addition, our model can understand multiple languages to intelligently execute actions where validation is required. For example, in a language quiz, our model can correctly select the right answer based on the question and answer shown. Similar to the previous point, this intelligence allows our explorer to cover more of an app thanks to more successful navigation attempts. Finally, we go over some characteristics of our UI dataset. Our dataset covers a wide range of apps from different categories, providing a well-rounded and comprehensive range of apps for a richer dataset. We also obtained more apps with a sub 4-star rating, which tend to be higher quality and more popular. The apps also vary in terms of their popularity based on the number of downloads on the Play Store. This also helps cover a wider range of apps. After all the refinement was completed, our dataset composed of 3,300 apps, spread across 33 different categories, including education, finance, food and drink, and many more. The apps in our dataset have an average rating of 4.17 stars and an average download count of 71 million. Initially, after the completion of our automated exploration, we had 46,000 UIs. After the automated screening processes, we were left with 22,000 UIs. Then, to further ensure the quality and accuracy of our dataset, our manual validation by humans left us with 18,000 UIs in our MUD dataset. Finally, let's explore some use cases of our dataset to show its potential as well as its practical improvement over existing datasets. The first application is UI element detection, or how our model can identify UI elements inside a screenshot. This application can be especially useful for accessibility features, helping guide users to make actions on screen or describing what's on a screen. To test this, we made an experimental setup. We trained a model using our dataset, using 70% of the dataset for training, 15% for validation, and 15% for testing. We also trained another model using the RICO dataset, where we used all of their dataset for training and used our test dataset for testing. In the numerous types of UI elements, the model trained using our dataset, MUD, consistently outperformed the model trained using the RICO dataset. This shows that our dataset is able to more accurately detect UI elements in current screenshots of apps. Here are some examples of the element detections. Our dataset can help train a model to identify complex UIs accurately. Another application is UI retrieval. Given a screenshot, how well can a model find the most similar looking screenshots from a dataset? This application can be useful for documentation or data archival purposes, allowing users to quickly and accurately retrieve certain UI elements from a set of UI designs. To test this, we trained two models, one using the RICO dataset and one using our dataset, MUD. We then fed both models screenshots, which subsequently returned what they believed were similar UIs. We then asked participants to rate the results of the 5 queried UIs from a dataset. Results showed a high relevance score of 4.1 for the model trained using our dataset, MUD, compared to a score of 3.2 using the RICO dataset. Our dataset is able to produce results that are more relevant and accurate. Here are a couple of examples of UI retrieval experiments we did, and a comparison between the RICO and MUD trained models' results. Overall, the model trained using our dataset is able to produce results with much more stylistic relevance, layout accuracy, and consistency. We're sure that there must be many more creative, innovative, and useful applications of our dataset that are yet to be explored. So we encourage everyone to take full advantage of our dataset to see what you can create. And that is it from me. I hope this presentation gave you a clear overview of how we employed innovative methods to create a UI dataset that is more relevant, less noisy, and more up to date, to keep up with our ever more data-driven and changing world. Our dataset is available on GitHub for use. We can't wait to see what applications our dataset will enable.